Okay, friends, let us discuss some important topics and questions for your plus 2 board exam. We are going to start with the topic of relations. Let us start with the very basic definition of a relation. If A and B are two non-empty sets, then a relation defined from set A to B is a rule which associates elements set A to the elements of set B. There is another definition for a relation. Relation R defined from A to B is any subset of the Cartesian product of the sets A and B. Now if set A has P elements, set B has Q elements, and the number of elements in set A cross P is going to be P into Q, that is PQ. And since relation is any subset of A cross B, so we know that for a set containing P into Q elements, the total number of subsets of A cross B are going to be 2 raised to power PQ, and hence the total number of relations from set A to B are 2 raised to power PQ. Let us take an example. Suppose a set A contains first 6 natural numbers, is 1, 2, 3, 4, 5 and 6, and a relation is defined on set A. Relation R is defined on set A, by which we mean that we are defining the relation from set A to A itself by R equals to A comma B such that B is equals to A plus 1 for all A and B belonging to set A. Now write R in the tabular form and hence find the domain and range of the relation R. Since we are defining the relation from set A to A itself, let us take an arrow diagram. This is set A containing 1, 2, 3, 4, 5 and 6. Again set A containing 1, 2, 3, 4, 5 and 6. Now since our relation says that element B is equals to A plus 1, means if I substitute A equals to 1 over here, B is going to be 1 plus 1, that is 2. So 1 is related to 2. Similarly 2 is related to 3, 3 is related to 4, 4 is related to 5 and 5 is related to 6. So my relation contains elements 1, 2, 2, 3, 3, 4, 4, 5 and 5, 6. If I want to define domain of a relation R, it is a set of all the first entries of the elements of the relation R. So first entries are 1, 2, 3, 4 and 5. So domain of the relation R is a set containing 1, 2, 3, 4 and 5. And range of relation R is a set of all the second entries of the ordered pairs. Second entries are 2, 3, 4, 5 and 6. So range of relation R is the set containing 2, 3, 4, 5 and 6. Now types of relation. Moving on to the main topic of the relations, it is type of relations. Let us start the first type, which is a reflexive relation. Now the definition says if a relation R is defined on set A, then if A comma A belongs to R or A is related to A for all or for every A belonging to the set A, then we say that R is a reflexive relation. Now there is an important note that in order to check whether a relation R is reflexive or not, we always check if it contains all the doublets for all the elements in the set A. Now let us take an example. If a set A contains 3 elements 1, 2 and 3, then check which of the following relations defined on A are reflexive. Now relation R1 is defined, which contains elements 1, 1, 2, 2 and 3, 3. Let us check whether R1 is reflexive. Now the definition says that if A comma A belongs to R for every A belonging to the set A. Now in this case set A contains 3 elements 1, 2 and 3 and all the 3 doublets are present in R1. So R1 is reflexive in nature. Let us move on to the relation R2. R2 contains 1, 1, 2, 2 and 1, 3. Now R2 is not reflexive in nature as 3 belongs to set A but 3, 3 is not present in R2, so this is not reflexive. Let's move on to the relation R3. R3 contains 1, 1, 2, 2, 3, 3, another element 1, comma 2. So as the definition says, corresponding to every element in set A, we need all the ordered pairs, and R3 contains all the 3 ordered pairs, and hence it is also reflexive in nature. Now, R1 and R3 are reflexive as they have all the doublets for every element of the set A. However, R2 is not, as it does not contain 3, 3 for 3 belonging to set A, and hence it is not reflexive in nature. Let us move on to the next type. Next type is a symmetric relation. Now, symmetric relation, if A comma B belongs to R, for A and B belonging to set A, then if B comma A belongs to set R, we say that R is a symmetric relation. Now, as the name suggests, symmetric word that for every A comma B belongs to R, we need the symmetric element B comma A belonging to R for R to be symmetric in nature. Let us take an example. If A is a set containing first 3 natural numbers 1, 2 and 3, then check which of the following 2 relations is symmetric or not. Now R1 contains 1, 1, 2, 1, 2, 3. Clearly 1 corresponding to 1, 2, 2, 1 is present in the relation, or 2, 1 corresponding to 2, 1, 1, 2 is present in the relation, but for 2, 3, 3, 2 is not present in this relation, so this is not symmetric. R2 is a relation which contains 1, 1, 1, 2, 2, 1, 2, 3, 3, 2. Now for 1, 1, we need 1, 1 which is itself present. For 1, 2, we need 2, 1 which is again present. For 2, 1, we need 1, 2 which is again present. For 3, 2, we need, for 2, 3, we need 3, 2, and for 3, 2, we need 2, 3. So this is a symmetric relation. So overall, R1 is not symmetric as 2, 3 belongs to R, but 3, 2 does not belongs to R, and R2 is symmetric in nature. Now let us move on to the third type, which is a transitive relation. Now if A comma B belongs to R and B comma C belongs to R, if A comma B belongs to R and B comma C belongs to R, for A, B and C belonging to the set A on which we are defining the relation, then if A comma C belongs to R, we say that R is a transitive relation. Now in this case we are transiting from A comma B element to B comma C, that is A comma to A comma C through the element B. So if such an element is present, or if our elements define this property, then we say that our relation is a transitive relation. Let us take an example to clarify the basic definition. Now if set A has elements 1, 2 and 3, then check which of the following relations defined on A are transitive. Now R1 is a relation which contains elements of the form 1, 2, 2, 3, 1, 3 and 3, 2. Now in this case, for the element 1, 2 and 2, 3, this element has second entry as 2, this element has first entry as 2, so we need an element of the form 1, 3 present in the relation, which is present over here. So we can say that this relation is transitive, but we need to check for all the elements present in this relation. For 2, 3 element belonging to R1 and 3, 2 belonging to R1, we need 2, 3, 3, 2, so I need 2, 2 element for this relation to be transitive in nature, but 2, 2 is not present in this relation, so this is not transitive. But for relation R2, it contains 1, 2, it contains 2, 3, it contains 1, 3, 3, 2 and 2, 2. Now for 1, 2 and 2, 3, I need 1, 3 which is present over here. For 2, 3 and 3, 2, I need 2, 2 which is again present over here. Now for every other element, for 3, 2 and 2, 2, I need 3, 2 which is again present. So this definition satisfies all the conditions of transitive relation. So this is transitive in nature. So overall, R1 is not transitive as 2, 3 belongs to R1 and 3, 2 belongs to R2, but 2, 2 does not belongs to R1, and R2 is a transitive relation according to the definition. Now let us As an important remark, a relation R which is reflexive, symmetric and transitive is called an equivalence relation. So this is the important type, that if our relation is reflexive, symmetric and transitive, we say that our relation is an equivalence relation. Now let us take few important examples as well as questions which are going to be the one which can be asked in your board exams. Let us take a first question. Now prove that relation R on the set Z of all integers defined by R equals to x comma y such that x minus y is divisible by n. Now for your board exams, n can be any number. It can be 2, it can be 3, it can be 4, it can be 5. So this is a general question which we are going to discuss, and we need to check whether it is we need to prove that this is an equivalence relation defined on the set of integers Z. So we are going to start with the first type of the relation. Let us check whether R is reflexive or not. So for reflexive, we need to check that all the doublets are present in this relation R. For the doublets, now since x comma x must be present, so let us see whether it is present or not. Now according to the definition, x minus y is divisible by n. This is the definition which relates elements of the relation x and y. As x minus x is 0, and we know that 0 is divisible by every number, so it is also divisible by n for every x belonging to the set Z. Therefore x comma x belongs to set R, and so R is reflexive in nature. So our first type is, it holds that R is reflexive in nature. Let us move on to the next one, symmetric. Now for symmetric, if x comma y belongs to R for x and y belonging to the set of integers, then according to the definition we have x minus y is divisible by n, as x comma y belongs to R. Now if x minus y is divisible by n, then y minus x is also divisible by n. Therefore y comma x belongs to R, and so R is symmetric in nature. So our relation is also symmetric in nature. Let us move on to the third type. Now for this one we need two elements in the relation. If x comma y belongs to R, and corresponding to this, if y comma z also belongs to R for x, y and z belonging to the set Z. Now as x comma y belongs to R, this means that x minus y is divisible by n according to the definition. So this can further be written as that x minus y is equals to n times q1, where q1 is any integer. So if x minus y is divisible by n, it means we can write x minus y equals to n times some q1, where q1 is an integer. Similarly, since y comma z belongs to R, so y minus z is also can also be written as n times q2, where again q2 is some integer. Now if I add these two equations, x minus y plus y minus z, so I'm going to get rid of y over here, and I'm going to get x minus y equals to n times q plus 1. So therefore x minus y is equals to nq, where q1 plus q2 is equals to q. This means that x minus y is divisible by n, and therefore x comma z is divisible by n. Therefore x comma z belongs to R, and so R is a transitive relation. Now as R is symmetric, we have proved this thing. We have proved that R is reflexive, R is symmetric and R is transitive, and hence R is an equivalence relation. That is what we need to prove, and I hope all of you got the method as well as the question properly. Let us move on to the next question. Show that each of the relation R in the set A. Now set A is the set containing x such that x is an integer and x is greater than or equal to 0 and less than or equal to 12. So it means we are dealing with whole numbers starting from 0 to 12. So set A contains 0, 1, 2, 3, 4 until 12. So this is my set A. Now relation is defined R equals to A comma B such that A minus B is a multiple of 4, as we have discussed earlier question. Now in this case we are particularly dealing with the number 4. And another relation we are defining on the set A itself, it is that A comma B such that A is equals to B, and we need to check whether it is an equivalence relation, and if it is an equivalence relation we need to find the set of all elements related to 1 in each of the case. Now let us start with the first question part. Now first part says R is equals to, R is a relation which contains elements of the form a comma b such that a minus b or mod of a minus b is a multiple of 4. Now if it is divisible by 4, if it is multiple of 4, or it is factor of 4, we are going to write the same solution for the question. Now according to this definition, a minus b is a multiple of 4. So relation R contains elements of the form 1 comma 5, as 1 minus 5 is minus 4. It is divisible by 4. 1 comma 9, as 1 minus 9 is 8, which is again divisible by 4. 2 comma 6, which means 2 minus 6 is 4, which is divisible by 4. And similarly all the other entries which satisfies this definition are present in this relation. So it contains elements 1 5, 1 9, 2 6, 2 10, 3 7, 3 11, 4 8, 4 12, 5 9, and hence so on, like this. Now for relation to be reflexive, we need to check that all the doublets are present in this relation. So in my case, a minus a in general is equals to 0, and we know 0 is divisible by every number, or 0 is a multiple of 4. So therefore a comma a is present, or a comma a belongs to R for all a belonging to set A. Therefore R is a reflexive relation. Let us move on for symmetric and transitive part. So for symmetric, if a comma b belongs to R for a and b belonging to the set A, this means that a minus b is a multiple of 4, which further means that b minus a is also a multiple of 4, and therefore for a comma b belonging to A, b comma a also belongs to set relation R, and therefore our relation R is symmetric in nature. Let us go for transitive part. We need elements of the form a comma b belonging to relation R, and b comma c belonging to relation R for a, b, and c belonging to set A. Now if a comma b belongs to R, that means a minus b is a multiple of 4, which means a minus b is equals to 4k1, and b minus c is also a multiple of 4, so mod of b minus c is equals to 4 times k2. Now if I add these two relations, now a minus b plus b minus c is equals to 4 times k1 plus 4 times k2, which is in all 4 times k1 plus k2, and hence a minus c is a multiple of 4, which means that if a comma b belongs to R and b comma c belongs to R, then a comma c, the transition element a comma c, also belongs to R, and therefore R is transitive in nature. And since R is reflexive, symmetric, and transitive, therefore our relation is also an equivalence relation. Okay. Now the question also demanded that we need to find the set which contains all the elements related to 1. Now according to the definition, it was that a minus b is divisible by, or a minus b is a multiple of 4. So multiple of 4. Now in my case, 1 minus 5 is a multiple of 4, so 1 comma 5 is related, or it is an element in this relation. Similarly 1 comma 9 also is equals to 8, so it is also a multiple of 4. So the elements related to 1 are 1 5 and 1 9. So that completes my first part. Second question is rather easy. It says that the relation R is defined by that it contains elements of the form a comma b such that a is equals to b. So in this case it will contain elements 0 0 1 1 2 2 and so on till 12 12. So it means all the doublets are present in this relation. Now in order to check whether it is reflexive, we need to check whether a comma a belongs to R, and since clearly a is related to a in this relation, so R is reflexive in nature. For symmetric part, if a comma b belongs to R, then b comma a must also belongs to R. Now in this case all the doublets are present in the relation, so it is an obvious case that for every a comma b belonging to R, b comma a also belongs to R, so R is also symmetric in nature. For transition, since a comma b belongs to R and b comma c belongs to R for this relation, now in this relation we have elements of the form 0 comma 0. Now this element is present in the relation. Now corresponding to this, there is no element which starts with 0 other than this itself. So it means for obvious reasons this relation satisfies the condition that if a comma b belongs to R and b comma c belongs to R, then a comma c belongs to R. So this says that is a comma c is also present in this relation, and hence R is transitive in nature. And since R is reflexive, symmetric, and transitive, hence R is an equivalence relation, and we need to find elements which are related to 1 under this relation, and clearly as 1 comma 1 is present in this relation, so 1, the related element to 1 is 1 itself, so it is a set containing element 1. Let us move on to next question. Now let us take next question. Prove that the relation R on n cross n. Now n cross n itself is a Cartesian product of set of natural numbers with itself, defined by a comma b related to c comma d by a plus d equals to b plus c. Now the definition says that we need to add the element a with d, and this must be equal to b plus c for all a comma b and c comma d belonging to the Cartesian product of n cross n. Now we need to check whether this is an equivalence relation or not, or we need to prove in this case, in fact, that this relation is an equivalence relation. So let us once again start with the reflexive part. It says that as a plus b is same as b plus a. Now for relation to be reflexive in nature, we need to show that a comma b is related to itself, that it must have a comma b related to a comma b. Now in this case, if I use the definition, I am dealing with a plus d, so in this case it will be a plus b. I need to check this thing. So a plus b is same as b plus a, because we know that addition of two real numbers or two natural numbers is commutative in nature. So a plus b is equal to b plus a, therefore ab is related to ab for all ordered pairs a comma b belonging to n cross n, and so R is reflexive in nature. For symmetric part, we need that if a comma b is related to c comma d. Now in this case, what we need to check, we need to show that c comma d is related to a comma b. Now according to the definition, a plus d is equals to b plus c. Now I can simply interchange my left hand side with the right hand side, so b plus c from the right hand side comes to the left hand side, and this is equals to a plus d. Now b plus c can also be written as c plus b, as addition is commutative in nature, and this is equals to d plus a. Now this shows that c is related to a and b is related to d. This means that c comma d is related to a comma b, and so R is symmetric in nature. It is symmetric in nature. Okay, so our relation is so far reflexive as well as symmetric. Now let us check whether it is transitive or not. Now if a comma b is related to c comma d in this relation, and c comma d is related to e comma f for a b c d and e comma f belonging to n cross n. Now according to the first definition, if ab is related to c comma d, that means a plus d is equals to b plus c, and if c comma d is related to e comma f, then c plus f is equals to d plus c, according to the definition of the relations, which was that a comma b is related to c comma d by a plus d equals to b plus c. Now according to this one, if a plus d is equals to b plus c, it means that a minus b is equals to c minus d. That is, bring b to the left hand side and take d to the right hand side, and similarly c minus d is equals to e minus f. Now I need to shift from ab to ef. It means I need to get rid of c and d from the definition. So in this case, a minus b is equals to c minus d, and c minus d is equals to e minus f. So therefore a minus b itself is equals to e minus f, which further implies that a plus f is equals to b plus e. Now if a plus f is equals to b plus e, this means AB is related to e comma f, and this is what we need to show in order to prove that R is transitive in nature. So R is a transitive relation, and hence R is an equivalence relation in our case. Now we have proved that R is reflexive, symmetric and transitive, so this is an equivalence relation. Let us move on to the next question. This is again an important and a potential question for your board exam. Now if a relation R is defined on set of real numbers, now this R represents set of real numbers, by a comma b such that a is less than or equal to b cube for every a and b belonging to the set of real numbers. Now we need to check whether R is reflexive or it is symmetric or transitive. Now let us start with the very first type, reflexivity or reflexive nature. Now in this case, the relation is defined on the set of real numbers. Now the real numbers are all the natural numbers, they are all the whole numbers. We can write it like this: natural numbers are subset of whole numbers are subset of your integers are your subset of rational numbers, and rational numbers plus the irrational numbers. Now this whole forms a set of real numbers. So in my case, I'm also dealing with rational numbers for the real number. Now as 1 comma 2 belongs to set of real numbers, but 1 comma 2 is not less than equal to 1 by 2 whole cube. Alright, so 1 by 2 is not less than equal to 1 by 8. So half comma half does not belongs to R. So this is not reflexive in nature. For symmetric part, as 1 comma 2 belongs to R, as we can easily guess that, check that 1 is less than equal to 8 or 2 cube for 1 comma 2 belong to the set of real numbers, but 2 comma 1 does not belongs to R, as 2 is not less than equal to 1 cube. So R is again not symmetric in nature for this definition of R. And for transitivity, we have that 10 comma 3 belongs to R, as 10 is less than equal to 3 cube, which is 27, and 3 comma 2 belongs to R, as 3 is less than equal to 2 cube, which is 8. But 10 comma 2 does not belongs to R, as 10 is not less than equal to 2 cube, that is 8. So R is not transitive in nature. So whenever we need to show whether R is not reflexive or it is not transitive or it is not symmetric, we simply going to give counter example to disprove something. This is important. And if I want to prove something, I'm going to start with the proper definition. So counter examples to disprove something and general proof to prove something. Right. So this completes our whole lecture for the relations. I hope you enjoyed the lecture, as well as you get to know the important concepts as well as important questions. So go through the whole lecture once again if you have any doubt, and we'll see you in the next lecture.